Right now, at the center of nearly every large galaxy in the universe, something is sitting in total darkness, bending the fabric of space around it, and quietly shaping the destiny of hundreds of billions of stars. You cannot see it. No light escapes it. No telescope on Earth can photograph its surface, because it has no surface at all. And yet this region of pure gravitational collapse, may be the single most important sculptor of the cosmos we live in. Black holes were once dismissed as mathematical curiosities, monsters too strange to be real. Today, we know they are everywhere, that one anchors our own galaxy, and that without them, the universe might look nothing like the structured, organized cosmos we see when we look up at the night sky. This is why a black hole, an object defined entirely by what it destroys, may actually be one of the great builders of everything around us. Before we begin, be sure to like the video and subscribe for more journeys into the cosmos. Now, take a deep breath and let's begin. To understand a black hole, you first have to understand what gravity really is. For most of human history, gravity was a mystery, dressed up as the obvious. Things fall down, apples drop from trees, rivers run toward the sea. It seemed like the simplest thing in the world, and for centuries nobody questioned why it happened. Then, a little over 300 years ago, the idea took shape that gravity was a force, an invisible pull reaching across empty space, tugging every object toward every other object. This picture worked beautifully. It predicted the orbits of planets, the paths of comets, the rise and fall of tides. It put spacecraft on the moon. But it was incomplete, and the gap in our understanding hid something extraordinary. A little over 100 years ago, a new vision of gravity emerged, one that changed everything. Gravity, it turned out, is not really a force pulling across empty space. Gravity is the shape of space itself. Imagine a stretched rubber sheet pulled tight, perfectly flat. Now place a heavy ball in the center. The sheet sags, forming a dip around the ball. Roll a marble nearby, and it curves toward the dip, not because the ball is pulling on it, but because the surface it rolls across is bent. This is what mass does to the universe. Every star, every planet, every grain of dust warps the space and time around it, and other objects move along those curves. The sun does not reach out and grab the Earth. Instead, the sun bends the space around it into a vast, invisible valley, and the Earth simply rolls around the inside of that valley, year after year, following the path of least resistance. What we feel as the pull of gravity is really the curvature of reality. And it is not only space that bends, time bends too. The two are woven together into a single fabric, a four-dimensional structure that physicists call space-time. When mass curves this fabric, it curves both the space and the time within it. This is one of the strangest and most counterintuitive ideas in all of science. And yet it has been tested again and again, always passing with flying colors. The satellites that power the navigation systems in your phone have to account for this very effect. The clocks aboard those satellites, sitting higher in Earth's gravity, tick at a slightly different rate than clocks on the ground. If engineers ignored this tiny difference, the navigation system would drift off by several kilometers within a single day. So every time you use a map on your phone, you are relying, without realizing it, on the fact that gravity bends time. This is not abstract philosophy. It is engineering fact, built into the technology in your pocket. Now hold that idea in your mind, because here is where things become strange. If mass bends space, then more mass bends it more steeply. A small planet creates a gentle dip. A massive star carves a deeper well. But what happens if you keep concentrating mass into a smaller and smaller space? The dip becomes a slope. The slope becomes a cliff. And if you cram enough mass into a small enough volume, the curvature becomes so extreme that the walls of the well turn vertical, then fold inward on themselves until they close off a region of space entirely from the rest of the universe. That sealed-off region is a black hole. It is not a thing in the way a star is a thing. It is a place where the curvature of space has become so severe that nothing, not even light, can climb back out. This is the crucial point that makes black holes so hard to imagine. We tend to picture a black hole as a giant cosmic vacuum cleaner, sucking everything around it into oblivion. That image is wrong, and it has confused people for generations. A black hole does not suck. If you replaced our sun with a black hole of exactly the same mass, the Earth would not be pulled in. It would keep orbiting in the very same path it follows now, because the gravity at our distance would be identical. The danger of a black hole is not that it reaches out to grab you. The danger is what happens when you get close, very close, to the point of no return. This is worth pausing on, because the misunderstanding is so common. A black hole at a distance behaves exactly like any other object of the same mass. Its gravity follows the same rules, fading with distance just as the gravity of a star or a planet does. If a black hole, the mass of the sun, suddenly appeared where the sun is now, the planets would not be devoured. They would carry on in their orbits, perhaps a little colder without the sunlight, but gravitationally undisturbed. The terrifying power of a black hole only reveals itself up close, in the tiny region near the event horizon, where the gravity grows so steep so quickly that escape becomes impossible. It is not a cosmic monster prowling space, hunting for victims. It is a quiet trap, dangerous only to whatever wanders into its immediate grasp. Understanding this distinction is the first step towards seeing black holes as they truly are, not as villains, but as natural consequences of the laws of gravity, as much a part of the cosmic order as stars and planets. That boundary has a name. It is called the event horizon. The event horizon is not a physical wall. There is nothing there to touch, no surface, no membrane, no shimmering barrier. It is simply a line in space that marks the threshold beyond which escape becomes impossible. Outside the horizon, if you fire your rockets hard enough, you can still pull away. Inside the horizon, no amount of power, no speed short of faster than light, and nothing travels faster than light, can save you. Once you cross that line, every possible path forward leads deeper in. The center of the black hole becomes not a place you can avoid, but a moment in your future as unavoidable as tomorrow. Think about that for a moment. Inside a black hole, falling toward the center is not a direction you can choose to resist. It is as inevitable as the passage of time itself. The geometry of space and time becomes so warped that the center, the singularity, lies in every direction you could possibly move. You cannot steer away from it any more than you can steer away from next week. This is why black holes are so unlike anything in ordinary experience. They are not objects sitting in space. They are regions where space and time themselves have been reshaped into something that no longer follows the rules we live by. Long before anyone understood the true nature of gravity, a handful of thinkers wondered what would happen if a star were massive enough that even light could not flee its surface. They called these hypothetical objects dark stars. Without light, they reasoned, such a star would be utterly invisible, betrayed only by its gravitational pull on the things around it. It was a remarkable guess, made with the crude physics of the time, and it turned out to be far closer to the truth than anyone could have known. These early thinkers imagined a star so large and so heavy that the speed needed to escape its surface would exceed the speed of light, and so the light itself would fall back down, trapped, leaving the star utterly dark to any distant observer. It was a brilliant intuition, even if the reasoning rested on ideas about light and gravity that would later be replaced. But the idea was forgotten for over a century, dismissed as a curiosity, until the modern understanding of gravity revived it in a far stranger and more rigorous form. When the new theory of gravity was published, just over 100 years ago, a young physicist, serving on the battlefront during a great war, worked out one of its first exact solutions. Within months, while ill and far from any laboratory, he found a precise mathematical description of the space around a perfectly round, non-spinning mass. Buried inside, his solution was something deeply troubling. At a certain distance from the center, depending on the mass, the equations seemed to go haywire. Quantities blew up to infinity. The mathematics appeared to break down completely. For years, physicists argued about what this meant. Was it a real feature of nature, or just a flaw in the coordinates, a mathematical illusion? It took decades to fully understand that this troubling distance was not a flaw at all. It was the event horizon, the boundary of a black hole, a real and physical threshold in the structure of space. And the most astonishing part is that the universe makes these things naturally, all the time, out of dying stars. To see how, we have to follow the life of a star from its birth to its final, violent collapse. A star is, at its heart, a constant battle between two opposing forces. To appreciate where black holes come from, you have to first understand that the stars themselves are not permanent. Every point of light you see in the night sky is a furnace, burning through its fuel, living on borrowed time. The most massive ones burn the brightest and the fastest, and they are the ones destined to become black holes. So the story of a black hole is, in truth, the story of a star living and finally surrendering to the one force it can never escape. On one side is gravity, always pulling inward, always trying to crush the star down into a smaller and smaller ball. On the other side is the outward pressure created by nuclear fusion in the star's core, where hydrogen atoms are fused into helium, releasing enormous energy. This energy pushes outward, holding the star up against its own crushing weight. For most of a star's life, these two forces are perfectly balanced. Our sun has held this balance for about 4.5 billion years, and it will hold it for roughly another 5 billion before things begin to change. This balance is what keeps a star stable, steady, and shining. But fusion requires fuel, and no star has an infinite supply. Eventually, the hydrogen in the core runs low. For a star like our sun, this triggers a series of dramatic changes. The core contracts, heats up, and begins fusing heavier elements. The outer layers swell enormously, and the star becomes a red giant, large enough to swallow the inner planets. Eventually, it sheds its outer layers gently into space, leaving behind a small, dense, slowly cooling core called a white dwarf. A white dwarf is incredibly dense. A single spoonful of its material would weigh as much as a truck. But it is not a black hole. Something holds it up, a strange quantum effect that prevents the electrons inside from being squeezed too close together. This quantum pressure is enough to support a white dwarf forever, as long as the star was not too massive to begin with. There is a precise limit to how much a white dwarf can weigh. Push it beyond a certain threshold, a little more than 1.5 times the mass of the sun, and even this quantum pressure fails. This limit was worked out by a young physicist on a long sea voyage, calculating in his cabin as the ship crossed the ocean. His conclusion, that the most massive stellar cores could not be held up by any known force and must collapse, was so radical that established scientists of the day mocked it and refused to take it seriously. It would be many years before the world understood that this young man had glimpsed the road that leads to black holes, and he would eventually be honored for that insight, long after his critics had been proven wrong. But our Sun is a relatively modest star. The truly massive stars, the ones 8, 10, 20, or more times the mass of the Sun, live very different lives, and they end them in ways that are almost beyond comprehension. A massive star burns hot and fast. Where our Sun will live for billions of years, a giant star may burn through its entire life in just a few million. It races through its hydrogen, then fuses helium into carbon, carbon into oxygen, and on through heavier and heavier elements, each stage burning faster than the last. In the final phase, the star is fusing silicon into iron, and this stage lasts only a single day, one day, after millions of years of life, and here the star meets a wall it cannot pass. Iron is special. It sits at a turning point in the nature of matter itself. Every element lighter than iron releases energy when fused together, and every element heavier than iron releases energy only when split apart. Iron is the ash at the bottom of the fire, the end of the line, the one element from which no more energy can be wrung by fusion. When a massive star builds up a core of iron, it has reached the final stage, with nothing left to burn. Fusing lighter elements releases energy, which is what holds the star up. But fusing iron does not release energy. It absorbs it. The moment the core becomes iron, the furnace shuts off. The outward pressure that has held back gravity for millions of years vanishes in an instant, and gravity, which has been waiting patiently the entire time, finally wins. The core collapses. In less than a second, a ball of iron larger than the Earth crushes down to a sphere just a few tens of kilometers across. The infalling material reaches speeds of tens of thousands of kilometers per second, nearly a quarter the speed of light. When the core can compress no further, the outer layers of the star, still falling inward, slam into it and rebound in a titanic explosion. This is a supernova, one of the most violent events in the universe. For a few weeks, a single supernova can shine brighter than an entire galaxy of hundreds of billions of stars. It scatters the elements forged inside the star, the carbon, the oxygen, the iron, out into space, where they will one day become new stars, new planets, and perhaps new life. The iron in your blood, the calcium in your bones, the oxygen you are breathing right now, all of it was forged inside stars and flung outward by these explosions. In a very literal sense, you are made of stardust. Every atom in your body, heavier than hydrogen, was cooked inside a star and scattered across space by one of these cataclysmic ends. The carbon in your cells, the gold in a wedding ring, the iron that gives your blood its color. None of it would exist without the violent collapse and explosion of massive stars. We are, all of us, the recycled remains of stars that lived and surrendered long before our sun was born. And in the heart of those same explosions, the universe was busy making something else, something that would outlast the stars themselves. But while the outer layers blast away into space, the collapsed core remains behind, and its fate depends entirely on how much mass it has. If the core is between roughly 1.5 and 3 times the mass of the Sun, the collapse halts at an extraordinary object called a neutron star. A neutron star is what happens when gravity crushes matter so hard that protons and electrons are forced together into neutrons, packing the entire mass of a star into a sphere only about 20 kilometers across. The density is almost impossible to grasp. A single sugar cube of neutron star material would weigh about 100 million tons, as much as the entire human population of Earth combined. A teaspoon of it would weigh more than a mountain. Neutron stars spin at incredible speeds, some rotating hundreds of times every second, sweeping beams of radiation across space like cosmic lighthouses. They are among the strangest objects we know of. And remarkably, we can watch them collide. In recent years, gravitational wave detectors caught the merger of two neutron stars. And unlike black hole mergers, this one also produced a brilliant flash of light that telescopes around the world rushed to observe. That single collision forged enormous quantities of heavy elements, including gold and platinum, and flung them out into space. It confirmed something astonishing, that much of the precious metal in the universe, perhaps even the gold in jewelry on Earth, was created in the violent collisions of these dead stellar cores. But they are still not black holes. Something still holds them up, a final form of quantum pressure between the tightly packed neutrons. It is the last defense matter has against total collapse. And if the core is too massive, that defense fails. When the collapsing core is more than about 3 times the mass of the Sun, no force in the universe can stop it. The quantum pressure that held up the white dwarf is overwhelmed. The neutron pressure that held up the neutron star is overwhelmed. There is nothing left. Gravity, unopposed, crushes the matter down past the point of a neutron star, past every known limit, smaller and smaller, denser and denser, until the curvature of space becomes infinite and a black hole is born. In that final instant, an object, the mass of several suns, vanishes behind an event horizon, sealing itself off from the rest of reality. The star that spent millions of years lighting up the cosmos becomes a region of pure darkness, a wound in space from which nothing can return. What lies at the very center, hidden inside the horizon, is something physics cannot yet describe. Our equations say that all the mass collapses into a single point of zero size and infinite density, a place called the singularity. But infinity is not really an answer. It is a signal that our current understanding has broken down. At the singularity, the smooth equations of gravity collide with the bizarre rules of the quantum world, and the two refuse to agree. We do not yet have a theory that can describe what truly happens there. It is one of the deepest unsolved problems in all of science, and it sits hidden at the heart of every black hole in existence. Think about what infinity really means here. The equations say the matter is crushed into a point of zero volume, which would make its density infinite, its gravity infinite, the curvature of space infinite. But nothing in the real universe is ever truly infinite. In every other branch of physics, when an equation spits out infinity, it is a warning sign, a flashing light telling us that our theory has been pushed past the edge of what it can describe. The appearance of infinity at the center of a black hole is the universe's way of telling us that something is missing from our understanding, that there is a deeper layer of physics we have not yet uncovered. Most physicists believe that the true center of a black hole is not actually a point of infinite density, but something more subtle, governed by laws we do not yet possess, laws that would unite gravity with the quantum world and tame those infinities into something finite and sensible. What that deeper reality looks like, no one yet knows. It may be that space and time themselves dissolve at the center, replaced by something we have no words for, a realm where the very concepts of here and now, of before and after, no longer apply. This is the frontier, the place where the boldest questions in physics are being asked. So the singularity remains a mystery, locked away forever behind the event horizon, beyond the reach of any experiment we can imagine. Before we go further, it helps to understand that black holes come in distinct families, separated by enormous gaps in size. At the smaller end are the stellar mass black holes, the kind born from the collapse of a single massive star. These range from a few times the mass of the Sun up to perhaps a few dozen times, and our galaxy is thought to contain hundreds of millions of them, scattered like dark seeds throughout its spiral arms. Most of these we will never detect, because they sit alone in the darkness, with no glowing matter falling into them to reveal their presence. They drift silently through the galaxy, invisible and unnoticed, betraying themselves only on the rare occasions when they happen to feed or to pass in front of a distant star. At the opposite extreme are the supermassive black holes, the true giants, millions to billions of times the mass of the Sun, dwelling at the centers of galaxies. Between these two extremes lies a strange and elusive middle ground. Black holes of intermediate mass, hundreds or thousands of times the mass of the Sun, should exist somewhere in between, but for a long time they proved frustratingly hard to find. They were the missing link, too big to form from a single star, too small to be the giants at galactic centers. In recent years, astronomers have finally begun to catch glimpses of these intermediate giants, often lurking at the hearts of dense star clusters. They may be the building blocks from which the largest black holes were assembled, the stepping stones in a process of growth that has played out over billions of years. Understanding these different families is the key to understanding how black holes shape the universe, because each plays its own distinct role in the cosmic story. What we can study is everything that happens outside, and that is where black holes reveal just how strange they truly are. Consider what would happen if you actually fell into one. Suppose you were falling feet first toward a black hole. As you got closer, gravity would pull harder on your feet than on your head, simply because your feet are closer to the center. This difference in pull is called a tidal force, and it is the same effect that creates ocean tides on Earth, where the moon tugs a little harder on the near side of our planet than the far side. Near a smaller black hole, this tidal force becomes monstrous. The difference in pull from one end of your body to the other would grow with every meter you fell, climbing from something barely noticeable to something utterly overwhelming in a matter of moments. The pull on your feet would so vastly exceed the pull on your head that you would be stretched out like a strand of spaghetti, drawn into a long, thin thread of matter. Scientists have a name for this, and it is exactly what you would expect. They call it spaghettification. You would be stretched lengthwise and squeezed from the sides at the same time, pulled apart atom by atom long before you ever reach the center. It is not a pleasant way to go. There is another feature of black holes that adds to their strangeness, and that is spin. Stars rotate, and when a star collapses, that rotation does not vanish. Instead, just as a spinning skater pulls in their arms and whirls faster, the collapsing core spins faster and faster as it shrinks. By the time a black hole forms, it can be spinning at a tremendous rate, with its event horizon dragging the very fabric of space around it like a whirlpool. This effect, where space itself is twisted and carried around by the rotation of the black hole, is one of the most exotic predictions of modern gravity, and it has real consequences. Near a rapidly spinning black hole, nothing can stay still. Space is dragged around so forcefully that an object would be swept along whether it wanted to be or not, forced to rotate with the black hole no matter how hard it tried to resist. Spin also changes the size of the region from which energy can, in principle, be extracted, and some physicists have imagined how an advanced civilization might one day harvest energy from a spinning black hole by carefully throwing matter into it and letting the rotation fling part of it back, out with extra energy. It sounds like science fiction, but it follows directly from the equations. A black hole, then, is described almost entirely by just three properties: its mass, its spin, and its electric charge. That is all. Everything else, about whatever fell in, all the complexity of the stars and gas and dust that formed it, is erased, hidden behind the event horizon. Physicists sometimes say that black holes have no hair, meaning they are astonishingly simple, smooth, featureless objects defined by just those three numbers. It is a strange thought that the most extreme objects in the universe are also among the simplest to describe. Two black holes with the same mass, spin, and charge are completely identical, no matter what wildly different things went into making them. One could have formed from a collapsing star, the other from a collapsing cloud of pure hydrogen, or a mountain of books, or anything at all. And once the dust settles, there would be no way to tell them apart. The black hole keeps no record of its past, only the barest summary of itself written in those three numbers. But strangely, around the largest black holes, the experience would be gentler, at least at first. The bigger a black hole is, the more spread out its gravity is at the event horizon, and the weaker the tidal forces there. If you fell into one of the truly giant black holes, the kind that lurk at the centers of galaxies, you could, in principle, cross the event horizon without feeling much of anything at all. You would sail past the point of no return without a single warning sign, no wall, no jolt, no flash of light. One moment you would be in the universe we know. The next, you would be sealed inside, with no way back, even though nothing around you had seemed to change. But the view on the way in would be like nothing else in existence. As you approached a black hole, the light around it would behave in deeply unfamiliar ways. The black hole's gravity is so strong that it bends the paths of light rays passing nearby, an effect called gravitational lensing. The stars and galaxies behind the black hole would not simply be blocked from view. Their light would be bent and smeared around the dark sphere, forming warped arcs and rings of distorted starlight encircling the blackness. You could, in a sense, see around the black hole, glimpsing objects that lie directly behind it, their images wrapped around the edge by the curvature of space. Closer still, the bending becomes so extreme that light can actually loop around the black hole one or more times before escaping, creating ghostly repeated images of the same stars, nested ring upon ring. The accretion disk, the glowing ring of matter circling the black hole, would appear strangely contorted, with the far side of the disk seeming to rise up above and below the black hole, as the light from behind it curves over the top and underneath, bent toward your eye. It would look as though the disk were folded around the darkness, an impossible shape that no ordinary object could ever produce. This is exactly the kind of view that careful simulations have shown, and it is one of the most beautiful and alien sights the universe has to offer. A place where light itself is forced to trace the warped geometry of space around the deepest gravity wells in existence. And here is where one of the most mind-bending features of black holes appears, something that has to do not with space, but with time. Near a black hole, time itself slows down. This is not science fiction. It is a direct prediction of how gravity works, and it has been confirmed by experiments here on Earth, where clocks at different altitudes tick at very slightly different rates. The stronger the gravity, the slower time flows. Near a black hole, where gravity is overwhelming, this effect becomes extreme. Imagine you stayed in a spaceship at a safe distance, while a friend bravely fell toward the event horizon. From your point of view, something very strange would happen. As your friend approached the horizon, you would see them moving slower and slower. Their clock would tick more and more sluggishly. The light from their ship would stretch out, shifting toward red, then dimming. And as they reached the very edge of the horizon, they would appear to freeze, hovering at the boundary, never quite crossing, their image fading until it was too faint to see. From your perspective, your friend would take an infinite amount of time to fall in. They would seem suspended at the edge forever. But from your friend's point of view, nothing unusual would happen at all. They would fall right through the horizon in a normal amount of time, perhaps just seconds, without noticing anything special at the boundary itself. Two observers, two completely different experiences of the same event, both equally real. This bizarre stretching of time has led some thinkers to imagine extraordinary possibilities. Because time slows so dramatically near a black hole, a traveler who ventured close to one and then returned would find that far more time had passed for everyone else. Imagine an astronaut who orbits near a supermassive black hole for what feels, to them, like a few hours. When they return to their home, they might find that years, or even centuries, had passed for the people they left behind. In a very real sense, this is a form of time travel into the future, and it follows directly from the proven physics of gravity. It is not science fiction. Clocks really do run slower in stronger gravity, and near a black hole the effect becomes extreme enough to leap across generations. The catch, of course, is that you can only travel forward in time this way, never back, and getting that close to a black hole safely would be a monumental challenge. But the principle is sound, written into the very structure of space-time. A black hole is, among everything else, a machine for bending time. This is what it means to say that black holes warp not just space, but time. They tear apart our intuition that there is a single, universal clock ticking the same way for everyone, everywhere. Near a black hole, time becomes personal, stretched and reshaped by gravity, and what feels like a moment for one observer can be an eternity for another. For a long time, all of this remained in the realm of theory. The mathematics predicted black holes, but many of the greatest minds in physics doubted they could really exist. Surely, they thought, nature would find some way to prevent such an absurd, infinite collapse. The very man whose theory predicted them spent years skeptical that real stars would ever actually form them. For decades, black holes were treated as a kind of mathematical embarrassment, a strange solution to the equations that probably had nothing to do with the real universe. That skepticism lasted until the evidence began to arrive, and once it started, it never stopped. The first hints came not from seeing black holes directly, which is impossible, but from watching what happens to matter around them. When gas and dust fall toward a black hole, they do not plunge straight in. Instead, they swirl around it, forming a flattened, spinning disk, much like water circling a drain before it goes down. This is called an accretion disk, and it is one of the most important features for finding black holes. Because while the black hole itself is invisible, the disk most certainly is not. As material spirals inward, it gets squeezed and crushed together, and friction heats it to staggering temperatures, millions of degrees. Matter that hot does not glow with ordinary light. It blazes in X-rays, a form of radiation far more energetic than visible light, pouring out from the region just outside the event horizon. So while you can never see the black hole, you can see the brilliant, superheated ring of doomed matter circling it, screaming in X-rays as it makes its final descent. The physics of these accretion disks is itself a marvel. As matter spirals inward, it does not simply fall, it loses energy gradually, friction within the disk, heating it more and more as it works its way toward the center. The innermost edge of the disk marks a special boundary, the closest stable orbit a particle can hold before it must inevitably plunge across the event horizon. Inside that boundary, there is no more orbiting, only the final fall. The matter in these disks reaches temperatures of millions of degrees, glowing not just in visible light but across the entire spectrum, from radio waves to the most energetic X-rays and gamma rays. The amount of energy released is extraordinary. Falling matter near a black hole can convert a far larger fraction of its mass into radiation than the nuclear fusion that powers the stars. This is what makes black holes, despite emitting no light of their own, among the brightest sources of energy in the entire universe, betrayed always by the agony of the matter they consume. In the 1960s and 1970s, astronomers began detecting powerful sources of X-rays scattered across the sky. One of the most famous was a source in the constellation Cygnus, the Swan, which became known as Cygnus X1. Studying it carefully, astronomers found a massive, hot star orbiting something invisible, something with the mass of about 15 suns packed into a region so small it could only be a black hole. The star and the unseen object were locked in a tight dance, and the black hole was stripping gas from its companion, pulling it into a blazing accretion disk that poured out the X-rays we detected. This is one of the most reliable ways to find a stellar mass black hole. You look for a visible star that appears to be orbiting nothing, circling an empty point in space, while X-rays pour out from the gap between them. The visible star betrays the presence of its dark partner through its motion and through the superheated gas being torn away and funneled toward the unseen companion. Many black holes in our galaxy have been found exactly this way, lurking in pairs with ordinary stars, slowly feeding on them across the ages. Cygnus X1 became one of the first objects widely accepted as a real black hole, transforming them from theoretical curiosities into established residents of our galaxy. The evidence for Cygnus X1 became so strong that it settled a famous wager between two of the greatest physicists of the era. One had bet that the object was not a black hole, partly, he later admitted, as a kind of insurance policy. If black holes turned out not to exist, at least he would have the consolation of winning the bet. But as the years passed, the case grew overwhelming, and he eventually conceded, acknowledging that Cygnus X1 almost certainly harbored a black hole. It was a lighthearted moment, but it marked a serious turning point. The scientific community had moved from doubting whether black holes existed at all to debating the precise mass of specific ones. The doubt was beginning to crumble. But these stellar mass black holes, the corpses of dead giant stars, turned out to be only the smaller members of a much larger family. Because hiding at the centers of galaxies, including our own, were black holes on a scale that nobody had imagined. For years, astronomers had noticed that something very strange was going on at the heart of our Milky Way galaxy. In a region called Sagittarius A, near the center of everything, stars were behaving in ways that made no sense unless something enormous and invisible was lurking there. So a team of astronomers did something extraordinary. They watched, for more than 2 decades, using the most powerful telescopes on Earth, they tracked the motions of individual stars orbiting the galactic center. And what they saw was astonishing. These stars were not drifting lazily. They were whipping around an invisible point at tremendous speeds. One star in particular, racing along a tight, elongated orbit, reached speeds of thousands of kilometers per second at its closest approach, moving faster than almost anything else known in the galaxy. This star completes a full orbit around the galactic center in about 16 years, swinging in close and then racing back out on a long looping path. For comparison, our Sun takes more than 200 million years to orbit the galaxy just once. This single star, by contrast, whips around its invisible companion in less time than it takes a human to grow from childhood to adulthood, and that is only possible because it is orbiting something almost unimaginably dense. At its closest approach, the star skims past the central object at a distance that, in cosmic terms, is a hair's breadth, and the only thing that could anchor such a furious orbit is a tremendous concentration of mass in a tiny space. For a star to move that fast, it had to be orbiting something with an immense gravitational grip. By carefully measuring these orbits, Astronomers could calculate exactly how much mass had to be hiding at the center to make the stars move the way they did. The answer was staggering. Concentrated into a region smaller than our own solar system was an object with the mass of about 4 million suns. 4 million suns crammed into a space where, if it were anything ordinary, we would surely see it. But we saw nothing. No bright cluster of stars. No giant glowing object. Just darkness. With millions of solar masses worth of gravity emanating from it, there was only one explanation that fit. A supermassive black hole sitting at the very center of our galaxy, anchoring the Milky Way and holding hundreds of billions of stars in its grip. The astronomers who made these painstaking measurements, tracking stars for decade after decade, were eventually awarded the Nobel Prize in Physics for this work. They had provided the strongest evidence yet that a monster truly does lurk at the heart of our galaxy. And the Milky Way is not unusual in this. As astronomers looked deeper, they found the same thing again and again. Nearly every large galaxy in the universe appears to have a supermassive black hole at its center. Some are far larger than ours. The black hole at the center of the galaxy, known as Messier 87, a giant elliptical galaxy in the Virgo cluster, holds the mass of about 6.5 billion suns. That is more than 1,000 times more massive than the one in our own galaxy. These supermassive black holes range from millions to billions of times the mass of the Sun, dwarfing the stellar mass black holes born from dying stars. The sheer scale of the largest is almost impossible to picture. The black hole in Messier 87 is so vast that its event horizon is larger than our entire solar system, larger than the orbit of the most distant planet around our Sun. Light, which crosses from the Sun to the Earth in about 8 minutes, would take the better part of a day just to travel across the width of this single black hole. And it is not even the largest known. Astronomers have found black holes weighing tens of billions of solar masses. Monsters so enormous that the numbers cease to mean very much, sitting at the centers of the largest galaxies in the universe. That these objects exist, that they are common, that nearly every great galaxy is built around one, was utterly unknown just a few generations ago. We have gone, in a single human lifetime, from doubting whether black holes were real at all to mapping a universe filled with them. And this raises one of the great puzzles in modern astronomy. How did they get so big? A black hole formed from a single dying star starts with only a few times the mass of the Sun. To grow to millions or billions of solar masses takes time, and growing them seems to require a lot of it. Yet astronomers have found enormous supermassive black holes that already existed when the universe was less than 1 billion years old, in cosmic terms, almost the very beginning. How did such giants form so quickly, so soon after the universe began? This remains an active mystery. Some scientists think the earliest black holes formed not from single stars, but from the direct collapse of huge clouds of gas, skipping the star stage entirely and starting out far more massive. Others think they grew by devouring matter at furious rates and by merging with one another over and over. The truth is, we are still working it out. The most powerful telescopes ever built are right now peering back toward the dawn of the universe, hunting for clues about how these ancient giants came to be. And the newest of these telescopes, the Great Infrared Observatory, now stationed far beyond the moon, has only deepened the puzzle. Peering further back in time than ever before, it has found galaxies and black holes that appear far more developed than they should be for such an early era. Some of these distant black holes are so massive, so soon after the beginning, that our standard ideas about how they grow simply cannot account for them. It is as though we expected to find seedlings and instead discovered towering trees. This has sent astronomers back to their theories, wondering whether the first black holes formed in some way we have not yet imagined, perhaps from the direct collapse of enormous gas clouds, or perhaps through processes in the infant universe that we are only beginning to understand. There is even a tantalizing idea that some black holes may have formed in the very first instance after the birth of the universe, not from stars at all, but from dense ripples in the chaotic early cosmos. These hypothetical primordial black holes, if they exist, could range from tiny to enormous, and some scientists have wondered whether they might even account for some of the mysterious, unseen matter that holds galaxies together. So far, this remains speculation, unconfirmed, but it shows how black holes keep turning up at the frontiers of our deepest questions. But however they formed, once these supermassive black holes existed, they did something remarkable. They began to shape the galaxies around them. And this is where the black hole transforms from a mere destroyer into something closer to an architect. For a long time, astronomers assumed that the central black hole was just a passive feature of a galaxy, a heavy lump at the middle that did not affect much beyond its immediate surroundings. After all, even a supermassive black hole is tiny compared to an entire galaxy. The black hole at the center of the Milky Way, despite its 4 million solar masses, is utterly dwarfed by the galaxy as a whole, which contains hundreds of billions of stars spread across 100,000 light-years. How could something so small, relatively speaking, possibly influence something so vast? To put the scale in perspective, if you shrank the entire Milky Way down to the size of a continent, the central black hole would be smaller than a single grain of sand sitting at its center. It seems absurd that such a speck could have any say over the fate of the whole. And yet, as astronomers gathered more and more evidence, they found that it does, in ways no one had anticipated. But then, astronomers discovered a strange and revealing relationship. When they measured the mass of the central black hole in many different galaxies, and compared it to the properties of the galaxies themselves, they found a tight connection. The bigger the black hole, the bigger the central bulge of stars around it, in a remarkably consistent ratio. This relationship was too clean, too precise, to be a coincidence. It strongly suggested that the black hole and its host galaxy grow up together, influencing one another, evolving as a connected system rather than as separate parts that happen to share a neighborhood. This connection has a name. Astronomers call it coevolution, the idea that a galaxy and its central black hole shape each other's destinies as they grow. It was a revelation, because it meant that to understand how galaxies form and change over cosmic time, you cannot ignore the tiny dark engine at the center. The black hole and the galaxy are partners in a relationship that has lasted for billions of years, each one constraining and guiding the other. This relationship holds across an astonishing range of galaxies, from modest spirals like our own to the largest ellipticals in the universe, always with that same consistent ratio between the mass of the black hole and the mass of the surrounding bulge of stars. The consistency is so striking that it has become one of the central clues in modern astronomy, a signpost pointing toward the deep connection between the smallest and the largest scales of cosmic structure. But how could a black hole, hidden at the center, possibly affect stars forming tens of thousands of light-years away? The answer lies in what happens when a black hole feeds. When a supermassive black hole pulls in large amounts of gas, that gas piles up in a swirling accretion disk and heats to extraordinary temperatures. The region becomes one of the most luminous things in the entire universe, an object called an active galactic nucleus. When the feeding is especially intense, this central engine can outshine all the hundreds of billions of stars in its galaxy combined. These are the objects we call quasars, and they are so brilliant that we can see them across nearly the entire observable universe, billions of light-years away. A single quasar, powered by gas falling into a black hole, can blaze brighter than 1,000 galaxies. The discovery of quasars was, in itself, one of the great mysteries of 20th century astronomy. When they were first found, astronomers were baffled. They appeared as faint points of light, looking almost like ordinary stars, which is why they were called quasi-stellar objects, later shortened to quasars. But when their distances were measured, the result was shocking. These points of light were billions of light-years away, near the edge of the observable universe. For something so distant to appear at all in our telescopes, it had to be releasing an almost unbelievable amount of energy, far more than any normal galaxy. How could a single object, no bigger than a solar system, outshine a galaxy of hundreds of billions of stars? For years it made no sense. The answer, when it finally came, was the black hole. Only matter falling into a supermassive black hole could release energy with such ferocious efficiency, converting a significant fraction of its mass directly into light. Burning fuel, the way stars do, is wildly inefficient by comparison. A black hole feeding on gas can extract many times more energy from the same amount of matter than nuclear fusion ever could. This is what makes quasars the brightest sustained objects in the entire universe. Beacons we can see across almost all of cosmic time. When we look at the most distant quasars, we are seeing light that left them when the universe was young. Light that has traveled for billions of years to reach our telescopes, carrying news of monstrous black holes feeding in the early cosmos. But the black hole does more than just shine. As matter spirals in and magnetic fields twist and tangle near the event horizon, something dramatic can happen. Not all the matter falls in. Some of it is flung back out, channeled into two narrow beams that erupt from the black hole's poles at nearly the speed of light. These are called relativistic jets, and they are among the most powerful phenomena in the universe. These jets can stretch for thousands, even millions of light years, reaching far beyond the boundaries of the galaxy itself. They blast outward like cosmic blowtorches, carrying enormous amounts of energy from the tiny central black hole out into the surrounding space, and even into the space between galaxies. The galaxy Messier 87, the same giant whose black hole we would one day photograph, displays one of the most famous of these jets. It is a brilliant blue streak of matter erupting from the galaxy's core, stretching across thousands of light years, so prominent that astronomers had noticed and puzzled over it for more than a century before anyone understood what powered it. That jet is matter being flung outward at nearly the speed of light by the supermassive black hole at the center, channeled and focused by twisting magnetic fields into a beam of astonishing precision and power. When these jets slam into the thin gas between galaxies, they inflate enormous bubbles and cavities, carving out structures hundreds of thousands of light-years across. In some galaxy clusters, astronomers have found gigantic cavities blown into the hot gas, evidence of black hole jets pumping energy outward over hundreds of millions of years. The amount of energy involved is staggering, equivalent to billions of stars detonating, all of it originating from a region smaller than our solar system. It is a humbling thought that an object you could never see, smaller than the space between the sun and the nearest planets, can reach out and reshape regions of space larger than entire galaxies. And it is these jets and this radiation that allow the black hole to act as an architect. When the black hole pours all this energy into its galaxy, it heats up the surrounding gas and drives it outward. This matters enormously because stars form from cold, dense clouds of gas that collapse under their own gravity. If you heat that gas up and blow it away, you shut down star formation. The black hole, in other words, acts like a thermostat for its galaxy. When it feeds intensely, it heats and expels the gas, choking off the birth of new stars. When the gas cools and begins to gather again, the black hole stirs back to life and pushes it away once more. In this constant give and take, the galaxy and its black hole settle into a long, slow equilibrium that plays out over the entire age of the universe. This is why the largest galaxies, the giant ellipticals with the biggest black holes, are often called dead. They have very little gas left to form new stars, having been blasted clean by the central black hole long ago. Their stars are old and red, with few young blue stars being born. You can actually see this difference when you look at galaxies across the universe. The lively spiral galaxies, full of cold gas, blaze with the blue light of young, hot stars constantly being born in their arms. The giant elliptical galaxies, by contrast, glow with the warm, reddish light of ancient stars, their gas long since heated and expelled, their star-forming days behind them. That difference, written in the colors of galaxies stretched across the sky, is in large part the signature of the black holes at their centers. The black hole essentially regulated the growth of its own galaxy, deciding, through its feeding and its outpouring of energy, how many stars that galaxy would ultimately make. Scientists call this process feedback, the way the black hole feeds on the galaxy's gas and then feeds energy back out into it, creating a self-regulating cycle. When too much gas pours toward the center, the black hole flares up and blasts that gas away, cutting off its own food supply and the galaxy's star formation at the same time. Then, with the gas expelled, the black hole quiets down again, until more gas eventually gathers and the cycle repeats. It is a remarkable balancing act, played out over hundreds of millions of years, with the tiny central black hole acting as a kind of cosmic regulator for the entire galaxy. This is a profound idea. It means the invisible, destructive object at the center of a galaxy is also one of the main forces controlling that galaxy's entire evolution, from a star-forming youth to a quiet, ancient maturity. Without the regulating influence of supermassive black holes, galaxies might have turned all their gas into stars far too quickly, growing into something very different from the galaxies we actually observe. The structures we see in the night sky, their sizes, their colors, their fates, all bear the fingerprints of the black holes hidden at their hearts. And the influence does not stop at the edge of a single galaxy. When galaxies collide and merge, as they often do over cosmic history, their central black holes eventually find each other and merge too, forming an even larger black hole. Our own Milky Way is on a collision course with the Andromeda Galaxy, our nearest large galactic neighbor. In about 4 billion years, the two galaxies will begin to merge, and over a long span of time, their central supermassive black holes will spiral together and unite into one. These cosmic mergers reshape galaxies entirely, transforming graceful spirals into vast featureless ellipticals, and the black holes at their centers play a central role in the violence and the energy of the process. Over billions of years, this dance of galaxies and the merging of their black holes has helped sculpt the large-scale structure of the universe itself. And the influence of black holes reaches even further than individual galaxies and their mergers. When you map out the entire universe on the largest scales, you find that galaxies are not scattered randomly. They are arranged in a vast, intricate pattern, an immense network of filaments and walls surrounding enormous, empty voids. This is called the cosmic web, and it resembles a three-dimensional spiderweb spanning the entire observable universe, with galaxies strung along glowing threads of matter. Black holes play a quiet but essential role in shaping this grand structure. By regulating how galaxies grow, by heating and expelling gas, by determining which galaxies keep forming stars and which fall dark. The black holes help decide how matter is distributed across this cosmic web. The brightest nodes of the web, the great clusters of galaxies, are kept in check by the energy that supermassive black holes pour into the surrounding gas. Without this regulation, these clusters would cool too quickly and collapse into far more stars than we actually observe. In this way, the smallest dark engines at the centers of galaxies leave their mark on the very largest structures in existence, stretching across hundreds of millions of light-years. The fingerprints of black holes are everywhere, woven into the architecture of the entire cosmos. When two black holes finally merge, they release a burst of energy unlike anything else, not as light, but as ripples in the fabric of space and time. These ripples are called gravitational waves, and their existence was predicted a century ago, in the same theory that first described black holes. For 100 years, they remained undetected, far too subtle to measure, a prediction that seemed forever beyond the reach of any instrument. A gravitational wave passing through you would stretch and squeeze you, but by an amount so unimaginably tiny that detecting it seemed impossible. We are talking about a change in length thousands of times smaller than the nucleus of an atom. To catch such a faint whisper from across the universe required one of the most precise instruments ever built. These detectors use laser beams traveling down long tunnels several kilometers in length, measuring the distance with such accuracy that they can sense a change far smaller than a single proton. And in the year 2015, after decades of effort, it worked. The detectors picked up a signal, a faint chirp rising in pitch over a fraction of a second. This signal had traveled for more than 1 billion years across the cosmos before reaching Earth. It was the unmistakable fingerprint of two black holes, each around 30 times the mass of the Sun, spiraling together and merging into one. The signal told an entire story in less than a second. In the beginning, the two black holes circled each other at a distance, slowly drawing closer as they radiated away their energy in gravitational waves. As they approached, they orbited faster and faster, whirling around one another hundreds of times per second in their final moments, sweeping closer and closer until they were nearly touching. Then, in a final violent instant, they collided and merged, the newly formed black hole ringing like a struck bell as it settled into its final shape. The whole drama, the inward spiral, the collision, the ringing aftermath, was encoded in the rising and then fading chirp. The detectors recorded a sound the universe had been broadcasting for over 1 billion years before anyone was able to hear it. In the final instant of their union, they converted an amount of mass equal to about 3 entire suns into pure gravitational energy, shaking the very fabric of the universe. For that brief moment, the power released by this single merger was greater than the combined light of every star in the observable universe. And yet it was completely invisible. No light, no flash, only a tremor in space-time itself, detected by listening to the shape of space as it rang like a bell. This discovery opened an entirely new way of observing the universe. The story behind that detection is itself a testament to human determination. For decades, building an instrument sensitive enough to catch a gravitational wave seemed like an impossible dream. Critics doubted it could ever work. The signal was simply too faint, the engineering challenge too extreme. But a dedicated community of scientists pressed on, building enormous detectors with arms several kilometers long, set at right angles to each other. Down these arms they fired laser beams, bouncing them back and forth between mirrors, suspended in near-perfect isolation from the vibrations of the world. When a gravitational wave passes through, it stretches one arm and squeezes the other by a fraction of the width of a proton, and the lasers can sense even that minuscule change. The detectors had to be shielded from everything, from earthquakes on the far side of the planet, from passing trucks, from the rumble of distant ocean waves, from the faint hum of the machinery itself. Two detectors were built far apart so that a real cosmic signal would register in both, while local disturbances would not. After years of refinement, the instruments reached the necessary sensitivity, and almost immediately the universe spoke. The very first confirmed signal arrived as the detectors were being tested, a clean and unmistakable wave from two black holes merging more than 1 billion light-years away. When the scientists first saw it, many could hardly believe it was real. It looked too perfect, too exactly like what the equations had predicted, but it was real, and it changed astronomy forever. For all of history, we had studied the cosmos by collecting light, from visible light to X-rays to radio waves. Now, for the first time, we could feel the universe through the vibrations of space and time, hearing events that emit no light at all. The team behind this achievement was awarded the Nobel Prize, and since that first detection, many more black hole mergers have been recorded, each one a confirmation that these invisible giants are real, that they collide, and that their collisions echo across the cosmos. But perhaps the most stunning confirmation of all came just a few years later, when humanity did something that had seemed impossible. We took a picture of a black hole. For most of the history of black hole science, the idea of photographing one seemed like a contradiction. A black hole emits no light. It is, by definition, invisible. How could you ever take its picture? The answer was clever. You cannot photograph the black hole itself, but you can photograph its shadow, the dark silhouette it casts against the glowing hot matter swirling around it. The bright accretion disk and the gas around a supermassive black hole would form a luminous ring, and in the center, where the black hole sits, there would be darkness, a perfect dark circle outlined by light, bent around it by the black hole's gravity. The challenge was that even the largest supermassive black holes appear incredibly tiny in our sky, because they are so far away. Photographing one would require a telescope the size of the entire planet. So astronomers built one. Not a single dish, but a network of radio telescopes scattered all across the Earth. From Hawaii to Chile, to the South Pole to Europe, all working together as if they were one enormous telescope as wide as the planet itself. By combining their observations with extraordinary precision, they could achieve the resolution needed to capture that tiny dark shadow on the other side of the universe. The target was the supermassive black hole at the center of the galaxy, Messier 87. That giant, with 6.5 billion solar masses, located about 55 million light-years away. It took an enormous team of scientists, vast amounts of data, and years of careful analysis to turn the raw signals into an image. And in the year 2019, they revealed it to the world. A glowing orange ring of superheated matter with a dark circular shadow at its center. It was the first direct image of a black hole ever captured, the silhouette of an object so massive and so distant that the light in the picture had left it millions of years before our own species existed. When that image was first revealed to the public, it became an instant icon, recognized around the world. A fuzzy orange ring with a dark heart. It may not have looked like much to the casual eye, but to scientists, it was breathtaking. Every feature of it matched the predictions of the century-old theory of gravity with remarkable precision. The size of the dark central region, the brightness of the ring, the way the light was bent and lensed around the unseen mass, all of it confirmed that this was exactly what a black hole should look like. The brighter part of the ring even revealed the direction in which matter was swirling around the black hole, with the side rotating toward us appearing brighter due to the way light behaves at such tremendous speeds. Producing this single image had required coordinating telescopes across continents, recording staggering amounts of data, so much that it could not be sent over the internet and instead had to be physically flown on stacks of hard drives to be combined. It took years of painstaking analysis by hundreds of scientists to transform that mountain of raw signals into one small, world-changing picture. A few years later, the same team produced an image of Sagittarius A, the supermassive black hole at the center of our own Milky Way galaxy. There it was, our own central monster, the 4 million solar mass object whose existence had been deduced from the orbits of stars, now seen directly as a ring of light surrounding a dark shadow. And our central black hole, for now, is relatively quiet. It is not feeding voraciously, not blazing as a quasar, just sitting there in a kind of slumber, occasionally nibbling on a passing cloud of gas. But every so often, anywhere in the universe, a supermassive black hole gets a sudden meal, and the result is spectacular. When a star wanders too close to a supermassive black hole, the tidal forces we spoke of earlier come into play on a stellar scale. The black hole pulls so much harder on the near side of the star than the far side that the star is torn apart, stretched into a long stream of glowing gas. This is called a tidal disruption event, and when it happens, about half the shredded star is flung away into space while the other half spirals into the black hole, briefly lighting it up in a flare that can outshine an entire galaxy for months. Astronomers have caught dozens of these stellar shreddings in recent years, watching from across the universe as black holes that had been dormant for ages suddenly flared to life, consuming an unlucky star that had strayed too near. Each one is a vivid reminder that these quiet giants are not truly asleep. They are simply waiting, and anything that drifts too close will pay the price. These images were not just beautiful, they were a triumph. They confirmed, in the most direct way possible, that the predictions made a century earlier were exactly right, down to the precise size and shape of the shadow. The theory had predicted what a black hole should look like, and when we finally looked, that is exactly what we found. The monsters were real, and they looked just as the equations had foretold. But for all that black holes seem like the ultimate one-way doors, the ultimate destroyers, there is one final twist in their story. One of the strangest and most beautiful ideas in all of physics. Black holes, it turns out, may not be entirely black after all. For decades, everyone assumed that a black hole was forever. Once formed, it could only grow, swallowing more and more matter, never giving anything back. Nothing escapes a black hole, the rule said, and so a black hole would simply persist for all eternity, getting larger and larger. But then, a brilliant physicist applied the rules of the quantum world to the edge of a black hole and discovered something no one expected. This happened in the early 1970s, and when the result first emerged, even the physicist who found it was surprised, and at first reluctant to believe it. He had set out to study black holes using the strange rules of quantum physics, expecting to confirm that nothing could escape them. Instead, the mathematics insisted that a black hole must glow ever so faintly, with a temperature that depends on its mass. It seemed to contradict the most basic definition of a black hole, and yet the calculation was sound, checked and rechecked. The smaller the black hole, the hotter it glows, and the faster it evaporates. The largest black holes are colder than the empty space around them, glowing so faintly that the radiation is, for now, utterly undetectable. But the principle was revolutionary. It united, for the first time, the physics of gravity, the physics of the quantum world, and the physics of heat, three great pillars of science, all meeting at the edge of a black hole. To understand it, you have to know a strange fact about empty space. According to quantum physics, completely empty space is not truly empty. It is constantly fizzing with activity, with pairs of particles popping into existence and then almost immediately annihilating each other, vanishing back into nothing. This happens everywhere, all the time, throughout the universe. These pairs appear and disappear so quickly that we normally never notice them. But now, imagine this happening right at the edge of a black hole, right at the event horizon. A pair of particles appears, just at the boundary. Normally they would meet again and vanish. But here, at the horizon, something can go wrong. One of the particles can fall into the black hole, while the other escapes outward into space. The escaping particle can never meet its partner again, so it cannot vanish. It becomes real, flying away from the black hole as genuine radiation. To balance the cosmic books, the particle that fell in must effectively carry negative energy into the black hole. And so the black hole loses a tiny bit of mass. Bit by bit, particle by particle, the black hole slowly gives up energy and shrinks. This faint glow of escaping particles is now called Hawking radiation, named after the physicist who predicted it. It means that black holes are not eternal after all. Over unimaginably long stretches of time, they slowly evaporate, leaking energy into space until, eventually, they disappear entirely. But this discovery led directly to one of the deepest and most troubling puzzles in all of physics, a puzzle that remains unresolved to this day. It is called the information paradox. Here is the problem. When something falls into a black hole, it carries information about itself. The precise arrangement of its atoms, the details of what it was. One of the most fundamental principles in physics says that this kind of information can never be truly destroyed. It can be scrambled, hidden, transformed, but in principle it must always be preserved somewhere. Yet, if a black hole slowly evaporates through Hawking radiation, and that radiation appears to carry no information about what fell in, then, when the black hole finally vanishes completely, the information seems to be gone forever. And that should be impossible. This is not a minor technicality. It is a genuine contradiction between two of our most cherished principles, the rules of black holes on one side and the rules of quantum physics on the other. For decades, brilliant minds have argued over how to resolve it. Some believe the information somehow escapes, subtly encoded in the radiation in ways we have not yet figured out. Others have proposed that the information is stored on the surface of the event horizon itself, like writing on a two-dimensional screen, in a strange idea suggesting that everything that falls in leaves an imprint on the boundary. This has led to one of the most radical ideas in modern physics, the suggestion that our entire three-dimensional universe might, in some deep sense, be encoded on a distant two-dimensional surface, like a vast cosmic hologram. It sounds absurd, and yet the mathematics of black holes keeps pointing in this direction, and many serious physicists now take the idea very seriously. The information paradox is still unsolved. But the very fact that black holes force us to confront such questions shows how central they have become to the deepest reaches of physics. But here is the truly astonishing part. This process is incredibly, almost absurdly slow for large black holes. A black hole, with the mass of the Sun, would take vastly longer than the current age of the universe to evaporate, not just a little longer, but a span of time so enormous that the numbers lose all meaning. For a supermassive black hole, the timescale is longer still, far beyond anything the human mind can grasp. In fact, these black holes are evaporating so slowly that right now they are still growing, absorbing more energy from the faint background radiation of the universe than they lose to evaporation. Only in the unimaginably distant future, when the universe has expanded and cooled far beyond its current state, will black holes finally begin to shrink in earnest. And this leads us to a vision of the very end of the cosmos, the final fate of everything. Far, far into the future, trillions upon trillions of years from now, the universe will be a very different place. The stars will have burned out. After the last of the gas is exhausted, no new stars will form. The existing stars will fade one by one until the galaxies go dark, filled with nothing but cold stellar corpses, dead white dwarfs, neutron stars, and black holes. The universe will enter a long, dark era, lit only by the faint glow of these remnants slowly cooling toward absolute darkness. To grasp how far into the future this lies, you have to abandon ordinary notions of time entirely. The universe today is about 14 billion years old. The era of starlight, the age we live in now, when galaxies blaze with the light of countless suns, is just the briefest opening chapter of cosmic history. It will end when the last stars burn out, perhaps 100 trillion years from now, a span so long that the entire age of the universe so far would fit into it thousands of times over. And even that is only the beginning of the darkness to come. After the stars fade, the universe enters an era that will last not for trillions of years, but for numbers so vast they can barely be written down, ages upon ages, in which almost nothing happens at all. In this distant epoch, the black holes will reign. They will be the last great structures in the cosmos, slowly drawing in the scattered remnants of dead stars, growing for a time as everything else fades around them. For an almost incomprehensible span of time, the universe will belong to the black holes, vast and dark and silent. But even they will not last forever. Across timescales so vast that the entire history of the universe up to now is less than a single heartbeat by comparison, the black holes will slowly evaporate through Hawking radiation. They will shrink, ever so gradually, leaking their mass away into the emptiness. And in the final stages, as a black hole grows small, its evaporation will speed up, until at the very end it vanishes in a final burst of energy, a last flicker of light in an otherwise dark and empty cosmos. After holding the universe together for so unimaginably long, after being the last great structures standing, the black holes will go out one by one, each ending its long reign in a brief final flash. It is a strange and poignant image. The final lights of the universe being extinguished not by the death of stars, but by the slow disappearance of the very objects that outlasted them all. When the last black hole finally evaporates, the universe will contain almost nothing, just a thin, cold haze of particles and radiation, spreading out forever into an endless, expanding darkness. The black holes, the last architects, will have built nothing more and finally crumbled away, leaving a universe with no structure at all. It is a sobering vision, the ultimate emptiness, with the black holes outlasting even the stars before they too fade into history. But that fate is so distant that it borders on the meaningless for us. We live in a young, vibrant universe, where black holes are not the lonely survivors of the end times, but the active sculptors of the cosmic structures we see. And in studying them, we are not just learning about exotic objects far away. We are learning about the deepest workings of reality itself, because black holes sit precisely at the crossroads of the two greatest theories in physics. On one side is the theory of gravity, which describes the very large, the curvature of space and time, planets, stars, and galaxies. On the other side is quantum physics, which describes the very small, the behavior of particles, and the strange fizzing of empty space. For nearly a century, these two theories have refused to fully agree with one another. Each works beautifully in its own domain, but when you try to combine them, the equations break down. This is not a small disagreement. It is arguably the single greatest unsolved problem in all of physics, a crack running straight through the foundations of our understanding of reality. Gravity describes a smooth, continuous, perfectly predictable universe of curved spacetime. The quantum world describes a jittery, probabilistic universe of discrete jumps and fundamental uncertainty. Both are spectacularly well tested. Both are, as far as we can tell, correct. And yet they cannot both be the final word, because they contradict each other in exactly the situations where both must apply. For nearly a century, the brightest minds in science have searched for a way to unite them, a single theory that would describe everything from the largest galaxy to the smallest particle in one consistent framework. This dreamed-of theory has a name, a theory of quantum gravity, and finding it is one of the holiest grails in all of science. And there is exactly one place in the universe where both theories must apply at once: inside a black hole. At the singularity, where an enormous mass is crushed into an unimaginably tiny space, you need gravity to describe the mass and quantum physics to describe the tiny scale. But the two theories give contradictory, nonsensical answers. This is why black holes are not just astronomical curiosities. They are natural laboratories for the deepest questions in physics, the place where our understanding fails, and therefore the place that may hold the key to a deeper, unified theory of everything. Many physicists believe that if we can truly understand what happens inside a black hole, we will finally discover how gravity and the quantum world fit together, completing a quest that has stretched across generations. The black hole, in this sense, is not the end of knowledge but a doorway to it. This idea of a doorway is more than just a metaphor. The very same equations that describe black holes contain, buried within them, hints of even stranger possibilities. If you take the mathematics at face value and follow it through, certain solutions seem to describe tunnels connecting one region of space to another, or even one universe to another. These hypothetical tunnels are called wormholes, and they have captured the imagination of scientists and storytellers alike. In principle, a wormhole could connect two distant points in space, allowing a shortcut between them, a kind of cosmic bridge. But there is a catch, and it is a serious one. The wormholes that emerge naturally from the equations are unstable. They would collapse the instant anything tried to pass through, snapping shut faster than light could cross. To hold one open would require some exotic form of matter with properties unlike anything we have ever observed, a substance with effectively negative energy. We do not know whether such matter can exist in the quantities required, and most physicists are deeply skeptical that traversable wormholes are physically possible. For now, they remain a fascinating consequence of the mathematics, a reminder that the equations of gravity hold mysteries we have only begun to explore. The equations also describe a strange mirror image of a black hole, something called a white hole. If a black hole is a region that nothing can escape, a white hole would be the reverse, a region that nothing can enter, spewing matter and light outward but never letting anything in. White holes appear in the mathematics as readily as black holes, and yet we have never seen one, and there are good reasons to think they cannot form naturally in our universe. Still, their appearance in the equations is a tantalizing hint of the symmetry hidden in the laws of nature. What all of this reveals is that black holes are not isolated oddities. They are deeply woven into the fundamental structure of physics, connected to questions about the nature of space, of time, of information, and perhaps of other universes entirely. And that is the strange, beautiful paradox at the heart of these objects. They are defined by darkness, by destruction, by the absence of light and the impossibility of escape. And yet they are among the most creative and important forces in the cosmos. They are the corpses of dead stars, and yet they anchor and shape entire galaxies. They destroy everything that falls into them, and yet they regulate the birth of new stars across hundreds of thousands of light years. They are invisible, and yet they have allowed us to feel the vibrations of space-time and to take pictures of shadows cast against the glow of doomed matter. They are the simplest objects in the universe, described by just a few numbers, their mass, their spin, and their charge, and yet they hide the deepest mysteries we know. When you look up at the night sky tonight, remember what is hiding in the darkness between the stars. At the center of our own galaxy, 4 million suns worth of mass sit crushed into a region of pure shadow, holding the Milky Way together, anchoring every star you can see, including our own sun, including the planet beneath your feet. We are, in a very real sense, in orbit around a black hole, carried along through the cosmos by a force we cannot see, and gravity we can only measure. Every star in our galaxy, every one of those hundreds of billions of suns, dances to the gravitational tune, set in part by that central darkness. The spiral shape of the Milky Way, the slow, majestic rotation of its arms, the long 200 million-year journey our own sun makes around the galactic center. All of it unfolds in the presence of that invisible anchor. And our galaxy is just one among trillions, each with its own dark heart, each shaped over billions of years by the unseen engine at its core. When you truly absorb this, the night sky transforms. The darkness between the stars is no longer empty. It is full of hidden mass, hidden structure, hidden engines of creation and destruction, working in silence across spans of space and time that dwarf anything in human experience. These invisible architects have shaped the galaxies, regulated the stars, sculpted the structure of the universe, and they hold within them the answers to questions we have only begun to ask. They are the darkest objects in existence, and yet by studying them, we are bringing the deepest secrets of reality into the light. The universe is built not only from the matter we can see in the stars that shine, but from these hidden engines of gravity, silent, invisible, and unimaginably powerful. The invisible architects of the cosmos. And the more we learn about them, the more we understand that the darkness is not empty at all. It is full of structure, full of meaning, and full of the most profound mysteries that science has ever encountered. We have journeyed from the bending of space around a falling apple to the collapse of dying stars, from the monster at the heart of our galaxy to the first image of a shadow cast against the cosmos, and on to the final, distant fate of everything that exists. And through it all, the black hole has stood at the center, dark and silent, shaping the universe around it. The next time you gaze into the night, know that you are looking out across a cosmos built, in no small part, by the things you cannot see. Every galaxy you could ever observe owes part of its shape, its size, and its story to a black hole at its heart. The stars that formed, the stars that never did, the great clusters held in balance, the merging galaxies and the rippling of space-time, all of it bears the quiet signature of these dark engines. They began as the corpses of dying stars and the seeds of the early universe, and they grew into the unseen foundations upon which the visible cosmos was assembled. For something defined entirely by darkness, by absence, by the impossibility of escape, the black hole turns out to be one of the most generative forces in all of nature. It destroys, and in destroying, it builds. It hides, and in hiding, it shapes everything we can see. And as we stand at the edge of our understanding, peering into these dark hearts, with telescopes spanning the planet and instruments that can feel the trembling of space itself, we are reminded that the universe still holds secrets vast enough to humble us and beautiful enough to draw us ever onward. Subscribe for more journeys into the cosmos, and remember, even in the deepest darkness, the universe is busy building.